Good morning, everyone. Uh, Today we are starting the new unit, new topic, which is Unit 5 Frequency Domain Analysis. Frequency Domain Analysis. As in the time domain analysis, we computed some parameters. On the basis of that parameters, we identified the system performance. We checked the system performance, system sensitivity on its roots, means how much sensitive the system is on its roots, and what is the performance of the system, right? What is the performance of the system? Similarly, as in time domain, in frequency domain also, there are some parameters that shows us the system performance. Some parameters that gives us the system performance, right? We can know about how fast our system is, how stable our system is on the basis of that parameters. So, as in the case of time domain, some parameters are there in frequency domain. Rather, the parameters used in time domain are not directly used in the frequency domain. There are some other parameters, but if I compute the frequency domain parameters, then separately we can tell anyone, we can say anyone about the system performance, about the system sensitivity, about the system stability, right? By using only frequency domain response. And as we know that the working with the frequency domain is much more easier than in the time domain, we have computed system performance in time domain just for LTI systems, just for small systems, less complicated systems. But as the complicacy of the system increases, we move forward to the frequency domain, right? We move forward to the frequency domain. And there are some parameters like resonance peak, resonant frequency, cutoff rate, and bandwidth. On the basis of these parameters, we can identify our system performance, right? And one more is stability. Right? So on the basis of these parameters, I can say about my system's performance, I can identify my system's performance, whether my system is fast or slow or stable or unstable, right? So let us consider, let the transfer function of a linear single input single output system be ms, then ys will be equal to ms into rs. Ys is equal to ms into rs, which is a convolution sum in the time domain, which is a convolution sum in the time domain, right? And we all know that the convolution sum is much more difficult in place of simple multiplication. In place of simple multiplication in frequency domain. And for sinusoidal steady state, replace S as j omega. For sinusoidal steady state, replace S as j omega, and then y of j omega becomes mj omega multiplied by r j omega. Mj omega multiplied by r j omega, right? The magnitude of this yj omega, magnitude and angle, if I find magnitude and angle of this yj omega, I am getting mj omega rj omega, and angle yj omega is equal to angle mj omega r j omega, right? And this will be equal to angle mj omega plus angle r j omega, and this will be equal to or less than or equal to mj omega magnitude of r j omega, right? Now, if I consider the magnitude of this input r j omega be r, and the angle of this r j omega is 0, then our magnitude becomes r magnitude mj omega, and angle is equal to angle of mj omega, right? So in frequency domain, I can break my output y of j omega in magnitude and angle form, and in combined form I can write yj omega as magnitude angle theta, where m is the magnitude of this yj omega, and theta is the angle of this yj omega, right? So whenever we apply frequency domain analysis, it is mandatory to write a system function in the form of magnitude and angle or in the polar form, right? Magnitude and angle or in polar form. Now, frequency domain specifications. Frequency domain specifications. First is resonant peak MR. Resonance peak MR. And what is the resonance peak? It is the maximum value of magnitude of mj omega a large MR correspond to a large maximum overshoot MP. जितना बड़ा MR होगा, जितना बड़ा रेजोनेंस पीक होगा, उतना बड़ा आपका मैक्सिमम ओवरशूट होगा, ठीक है? सेकेंड इज resonant frequency omega r. Resonant frequency omega r. It is the frequency at which the resonance peak MR occurs, at which the resonance peak occurs. Next is bandwidth. Bandwidth. BW. What is bandwidth? Bandwidth is the range of frequencies. What is bandwidth? Bandwidth is the range of frequencies, right? So, the bandwidth is the frequency at which the magnitude of mj omega drops to 70.7% of, or 3 dB down from its zero frequency value. So what is bandwidth? What is bandwidth? Bandwidth is the frequency at which the magnitude drops to 70.7% or 3 dB down from its zero frequency value. This bandwidth is also called cutoff frequency. This bandwidth is also called cutoff frequency. And this is the range of frequency. Bandwidth, what is bandwidth? Bandwidth is the range of frequency up to which the magnitude of the mj omega remains more than 70.7%. Remains more than 70.7%. This is the bandwidth. A large bandwidth corresponds to a faster rise time. Corresponds to a faster rise time since higher frequency signals are more easily passed through the system. A large bandwidth corresponds to a faster rise time. Obviously, frequency will be higher, time will be lower. So, large bandwidth corresponds to a faster rise time since higher frequency signals are more easily passed through the system. जब हायर फ्रीक्वेंसी सिग्नल्स इजीली पास हो जाएंगे आपके सिस्टम से, तो इसका मतलब है कि उसमें टाइम डिले बहुत कम है और आपका राइज टाइम बहुत छोटा है. ठीक ना? बहुत फास्ट है राइज टाइम. कन्वर्सली, if the bandwidth is small, only signals to relatively low frequencies signals of relatively low frequencies are passed and the time response will be slow. and the time response is slow, right? So for large bandwidth, rise time is small, and for small bandwidth, rise time is very high. And small rise time makes the time response faster, and the large rise time makes the time response slower, right? Next is cutoff rate. Cutoff rate. Sometimes it is necessary to look at the slope of magnitude of j omega to indicate the ability of a system in distinguishing signals from noise, which is called the cutoff rate of the frequency response. Cutoff rate of the frequency response. So, what is the cutoff rate of the frequency response? The slope of the magnitude mj omega is the cutoff rate of the frequency response, right? So, let us determine the resonance peak, resonant frequency, and bandwidth of the frequency response. Mr omega r and bw of frequency response or frequency response parameters. So let us consider a closed loop transfer function of a prototype second order system as ms is equal to ys over rs is equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. And at sinusoidal steady state, this ms can be written as mj omega, which is equal to yj omega over rj omega, which is equal to omega n square divided by j omega square plus 2 zeta j2 zeta omega n omega plus omega n square, or 1 by minus omega by omega n square plus 2 j2 zeta omega by omega n plus 1, or 1 divided by 1 plus j2 zeta, or 1 minus omega by omega n square plus j2 zeta omega by omega n, right? And let omega by omega n is equal to a variable u. Let omega by omega n is equal to a variable u, then m of u will be equal to 1 by 1 minus u square plus j2 zeta u. The magnitude of this mu is equal to magnitude of this u, or mju, let's write it as mju, is 1 over under root 1 minus u square whole square plus 4 zeta square u square. And the angle mju is equal to minus tan inverse 2 zeta u divided by 1 minus u square, right? So we have magnitude and angle of this mju, and for resonant peak we will find the maxima of this magnitude. Let us write it as m. What will be the maximum value of m? So for finding the maxima of this m, we'll take first derivative of m, dm by du, and make it equal to 0. And after solving, we get u is equal to 0 and under root 1 minus 2 zeta square. U is equal to 0 and under root 1 minus 2 zeta square. And at u is equal to 0, omega becomes 0. At u is equal to 0, omega becomes 0. And if zeta is less than 0.707, if zeta is less than 0.707, then it is not the true maximum. Then it is not the true maximum, because for zeta less than 0.707, for zeta less than 0.707, we have another maximum, right? For zeta less than 0.707, we have another maximum, right? So the resonant frequency becomes u is equal to under root 1 minus 2 zeta square, and u is equal to omega by omega n. So omega becomes, or omega r becomes, omega n under root 1 minus 2 zeta square. Since at this value of u we never find the true maximum, so the next value of u is this, at which we can find the true maximum, right? We find the true maximum, and the true maximum will be at omega is equal to omega r, which is equal to omega n under root 1 minus 2 zeta square. So this is the resonant frequency. And what is the resonant peak? The value of magnitude at this resonant frequency, the value of magnitude at this resonant frequency will be the resonant peak, will be the resonant peak, right? And the resonant peak is mr is equal to magnitude of mju, where u is equal to under root 1 minus 2 zeta square. 1 minus under root 1 minus 2 zeta square. And as I put this value here, I am getting here 1 minus 1 plus 2 zeta square. So 4 zeta, 4 plus 4 zeta square minus 8 zeta 4, and this will be equal to 1 divided by 4 zeta square minus 4 zeta 4, which is equal to 1 by 4 zeta square, and this is all power 1 by 2. 4 zeta square 1 minus zeta square whole power 1 by 2, and thus this becomes 2 zeta under root 1 minus zeta square. This is MR. MR becomes 1 by 2 zeta under root 1 minus zeta square, and omega R becomes omega n under root 1 minus 2 zeta square, right? And this is true for zeta less than 0.707, and this is true for zeta less than 0.707, right? So we can make a table here. Zeta is less than equal to 0.707 and zeta greater than 0.707, omega R and MR. For less than equal to 0.707, omega R is equal to omega n under root 1 minus 2 zeta square, and MR is 1 by 2 zeta under root 1 minus zeta square. And for zeta greater than 0.707, omega R is always 0 and MR is always 1. Omega R is always 0 and MR is always 1. Right? Now, next is bandwidth. Bandwidth. As per the definition of the bandwidth, the magnitude of MJU should be equal to 0.707, should be equal to 0.707 or is equal to 1 by under root 2, is equal to 1 by under root 2, right? So on solving, 1 over 1 minus u square whole square plus 2 zeta u square power 1 by 2 is equal to 1 by root 2. On solving this, we get u is equal to 1 minus 2 zeta square plus 4 zeta 4 minus 4 zeta square plus 2 under root whole power 1 by 2. And since u is equal to omega by omega n, so omega, which is equal to bandwidth, is equal to omega n within bracket 1 minus 2 zeta square plus under root 4 zeta 4 minus 4 zeta square plus 2 whole power 1 by. This is our bandwidth. So in the next lecture, the next video, we'll move forward to the next topic. Thank you.